Today's video is on describing motion using computational and applied math. We often have simple formulas to describe our motion.
An object traveling in one dimension at constant velocity. We have a formula for that. X equals velocity times time.
An object moving at constant acceleration. We have a formula for that.
How about a projectile fired from a cliff in 2 dimensions? We have formulas for that also. Now, how about many particles of different size, mass, velocity, acceleration, etc., all moving in 3 dimensions?
We have no simple math to solve that.
Our projectile problem, we simplify our math. First, we calculate a velocity of y at any given time t, using that the velocity of y at t equals the velocity of y at t minus 1 plus a times dt, where dt is the change in time between observations. Now we find y sub t equals y sub t minus 1 plus v sub t minus 1 dt. The object moves at v sub t minus 1 from time t minus 1 to time t.
Now let's see how our model compares to the actual data using math. We're first going to plot the actual data using the formulas in blue. Next, we're going to plot our first run of the model with a large dt in green, and we'll see that the graph comes out a little bit above the original actual math. Then we use a smaller dt in black, and we plot this, we'll see it comes closer to the actual values. By making the time interval smaller, our simulation becomes a better approximation of the real world. There's less error. The downside of decreasing dt is it increases the time that it takes to run the model. The net is, by improving our models, we can simulate complex situations which we cannot solve mathematically, all through computational and applied mathematics.